Computer Arithmetic. Learning Objectives. In this chapter, the user would learn the following in detail. Addition and subtraction with signed magnitude data. Multiplication algorithms, hardware algorithm and Booth algorithm. Division algorithm. Introduction. Arithmetic instructions perform arithmetic operations and are responsible for the data processing in the computer. The basic arithmetic operations are addition, subtraction, multiplication and division. Addition and subtraction with signed magnitude data. Signed magnitude number. A signed magnitude number Z can be represented as A subscript S A, where A subscript S is the sign of Z and A is the magnitude of Z. The leftmost position A subscript S is a sign bit. The sign bit is either positive, which equals 0, or negative, which equals 1. 8 conditions for signed magnitude addition subtraction. Table shows the conditions for signed magnitude addition subtraction. Example: addition, subtraction. Example of adding two magnitudes when the result is a sign of the larger magnitude. Flowchart of addition and subtraction with signed magnitude data. Shows the flowchart of addition and subtraction with signed magnitude data. Summary of addition and subtraction with signed magnitude data. The signs use an exclusive OR gate where if the output is 0, then the signs are the same. Hence, add the magnitudes of the same sign numbers. If the sum is an overflow, then a carry is stored in E, where E equals 1, and transferred to the flip-flop AVF, add overflow. Otherwise, the signs are opposite and subtraction is initiated and stored in A. No overflow can occur with subtraction, so the AVF is cleared. If E equals 1, then A is greater than or equal to B. However, if A equals 0, then A equals B and the sign is made positive. If E equals 0, then A is lesser than B and sign for A is complemented. Addition and subtraction with signed magnitude data hardware design. Shows the hardware design of addition and subtraction with signed magnitude data. Algorithm. A finite number of well-defined procedural steps are called an algorithm. Data can be in any of these types. Fixed point binary data in signed magnitude representation. Fixed point binary data in signed 2's complement representation. Floating point binary data. Binary coded decimal BCD data. There are 3 ways to represent negative fixed point binary numbers: signed magnitude form, signed 1's complement, and signed 2's complement representation. Signed 2's complement is used mostly in computers for floating point operations. Most computers use the signed magnitude representation for the mantissa. When two signed magnitude values are added or subtracted, the possible alternates are: the last column is needed to prevent a negative 0. The algorithm for addition or subtraction can be derived from the above table. Signed magnitude form. We designate the magnitude of two numbers A and B. When the signed numbers are subtracted or added, we find that there are 8 different combinations to consider depending on the sign of the number and the operation to be performed. When performing add operation, consider the 4 cases. Case 1. When A and B both are positive and performing addition operation, add the two numbers directly, attach A's operand sign. Case number 2. When both the operands are negative and performing addition operation, add the two numbers, append the result with A's operand sign. Case number 3. When A is negative and B is positive, when performing subtraction operation, find A plus B directly, attach A's operand sign. Case number 4. When A is positive and B is negative, when performing subtraction operation, add the two operands directly, attach A's operand sign. When the signs of A and B are identical, different, add the two magnitudes and attach the sign of A to the result. When the signs of A and B are different, identical, compare the magnitudes and subtract the smaller number from the larger. Choose the sign of the result to be the same as A if A is greater than B, or the complement of the sign of A if A is lesser than B. If the two magnitudes are equal, subtract B from A and make the sign of the result positive. Hardware implementation. The procedure for addition and subtraction requires a parallel adder for performing addition operation. Complemented is used to perform 1's complement of B register and E flip-flop. The mode M signal is also applied to the input carry of the adder. When M equals 0, the output of B register is directly transferred to parallel adder plus the input carry is 0. Using A register, content addition operation is performed and result transferred to A register itself. If carry occurs in addition operation, it is transferred to AVF flip-flop. When M equals 1, the 1's complement of B is applied to the parallel adder with input carry 1. That is, complement of B plus 1, 2's complement of B. So the result is A plus 2's complement of B, A minus B. Addition and subtraction with sign magnitude data. Hardware implementation. A's and B's are compared by an exclusive OR gate. If the output of the gate is 0, the signs are identical. If it is 1, the signs are different. For an add operation, identical signs dictate that the magnitudes be added. For a subtract operation, different signs dictate that the magnitudes be added. In both the cases, the result will be stored in EA register. When carry occurs, E flip-flop value is transferred to AVF flip-flop. The magnitudes are subtracted by adding A to the 2's complement of B. No overflow can occur if the numbers are subtracted, so AVF is cleared to 0. A1 in E indicates that A is greater than or equal to B, and the number in A is the correct result. If this number is 0, the sign A must be made positive to avoid a negative 0. A0 in E indicates that A is less than B. Hence, 2's complement of A is taken and the sign of the result is the complement of the original sign of A. The final result is stored in register A and its sign is A's. AVF indicates overflow and E is discarded. Addition and subtraction by signed 2's complement data. Comparing to the signed magnitude algorithm, this algorithm is much simpler to add and subtract numbers if negative numbers are in signed 2's complement representation. In this 2's complement representation, the leftmost bit represents the sign bit, 0 for positive and 1 for negative. If the sign bit is 1, the entire number is represented in 2's complement form. For the addition of two numbers, the numbers are added with the sign bits treated the same as the other bits of the number. A carry-out of the sign bit position is discarded. For the subtraction, minuend is added to the 2's complement of subtrahend. Hardware implementation. Sign bits are not separated, hence 2 register AC and BR has the values and leftmost bits represent the sign of the values. The values are added or subtracted in the complemented and parallel adder with the sign bits. The overflow flip-flop V is set to 1 if there is an overflow. the output carry is discarded. Algorithm and flowchart. The algorithm for adding and subtracting two binary numbers in sign 2's complement representation is shown above. Addition is done by adding the contents of AC and BR, including the sign bit. The overflow bit V is set to 1 if the XOR of the last two carries is 1 and it is cleared to 0 otherwise. The subtraction is carried by adding the content of AC to the 2's complement of BR. If the signs are same, overflow must be checked. Multiplication algorithms, hardware algorithm. The manual process multiplying two fixed-point binary numbers is given. If the least significant bit of multiplier is a 1, the multiplicand is copied down, else zeros are copied down. The copied down numbers are shifted one position to the left from the previous number. Finally, the numbers are added, which gives the product. The sign of the product is determined from the signs of the multiplicand and multiplier. If they are identical, the sign of the product is positive. Negative if they are different. Multiply algorithm version 1 shows the flowchart for multiply algorithm version 1. Multiplication hardware 1 shows the flowchart for multiplication hardware 1. Multiplication hardware. Product initialized to all zeros. Control decides when to shift the multiplier and multiplicand registers and when to write new values to product register. At the end, the multiplier is out of the product register and the product contains the result. Step-by-step transition in the registers during the multiplication process 1. Changes can be made. Instead of shifting multiplicand left, shift product right. Adder can be shortened to length of the multiplier and multiplicand, 8 bits in our example. Place multiplier in right half of the product register. Multiplier will disappear as product is shifted right. Add multiplicand to left half of product. Multiply algorithm final version shows the flowchart for multiply algorithm final version. Multiplication hardware final shows flowchart for multiplication hardware final. Multiplication of signed magnitude data hardware implementation. The manual process is slightly changed and implemented with the computer. First, instead of keeping register to store and add simultaneously as many numbers as there are bits in the multiplier, it is convenient to provide an adder for adding only two binary numbers and successively accumulate the partial products in a register. Second, instead of shifting the multiplicand to the left, the partial product is shifted to the right, which results in leaving the partial product and the multiplicand in the required positions. Third, when corresponding bit of the multiplier is 0, there is no need to add all zeros to the partial product since it will not alter its value. The multiplicand is in register B and the multiplier in Q and its signs in BS and QS. The sequence counter in SC, which has the number of digits in multiplier. The sequence counter is decremented by 1 after forming each partial product. When it reaches 0, the product is formed and the process ends. SHR, EAQ designate the right shift. The LSB of A is shifted into the MSB of Q. The bit from E is shifted into the MSB of A and 0 is shifted into E. Algorithm and flowchart. Initially, A and E are cleared and the SC with the number of bits in the multiplier and signs are checked. The QN bit of the multiplier is tested. If it is 1, the multiplicand in B is added to the present partial product in A. If it is 0, nothing is done. Register EAQ is shifted right once at end of each operation. If the SC is not equal to 0, the process is repeated until it reaches 0. Final product is available at AQ. Algorithm example. Table shows an example of multiplication of signed magnitude algorithm. Booth algorithm. Main difficulty arises when signed numbers are involved. Naive approach. Convert both operands to positive numbers, multiply, then calculate separately the sign of the product and convert if necessary. A better approach, Booth's algorithm. Booth's idea. If during the scan of the multiplier we observe a sequence of ones, we can replace it first by subtracting the multiplicand instead of adding it to the product, and later add the multiplicand. Example: 0110 multiplied by 0011, 6 into 3. This can be done by 8 minus 2 into 3 as well, or 1000 minus 0010 multiplied by 0011 using 8-bit words. At start, product equals 00000000. Looking at each bit of the multiplier 0110 from right to left. 0, product unchanged, 00000000, shift multiplicand left, 00110. 1. Start of a sequence. Subtract multiplicand from product 00000000 minus 00110, which equals 11111010. Shift multiplicand left 001100. 1. Middle of sequence. Product unchanged 11111010. Shift multiplicand left 00110000. 0. End of sequence. Add multiplicand to product 11111010 plus 00110000 equals 00010010, which equals 18. Shift multiplicand left 00110000. Booth multiplication algorithm. Multiplication of 2's complement values. Booth algorithm operates on the fact that strings of zeros in the multiplier require no addition but just shifting, and a string of ones in the multiplier from bit weight 2k to 2m can be treated as 2k plus 1 minus 2m. For example, the binary number 001110 plus 14 has a string of ones from 23 to 21. K equals 3, m equals 1. The number can be represented as 2k plus 1 minus 2m, which equals 24 minus 21, which equals 16 minus 2, which equals 14. Therefore, the multiplicand m into 4, where m is the multiplicand and 14 the multiplier, can be done as m into 24 minus m into 21. Thus, the product can be obtained by shifting the binary multiplicand m 4 times to the left and subtracting m shifted left once. As in multiplication, Booth algorithm requires examination of the multiplier bits and shifting of the partial product. Prior to the shifting, the multiplicand may be added to the partial product, subtracted from the partial product, or left unchanged according to the following rules. The multiplicand is subtracted from the partial product upon encountering the first least significant one in a string of ones in the multiplier. The multiplicand is added to the partial product upon encountering the first zero in a string of zeros in the multiplier. The partial product does not change when the multiplier bit is identical to the previous multiplier bit. The algorithm works for positive or negative multipliers in 2's complement representation. This is because a negative multiplier ends with a string of ones and the last operation will be a subtraction of the appropriate weight. For example, a multiplier equal to -14 is represented in 2's complement as 110011 and is treated as -24 plus 22 minus 21, which equals -14. Multiplication of 2's complement values, hardware implementation. This algorithm gives a procedure for binary integers in signed 2's complement representation. When the LSB of QR register and QN+1 flip-flop is used to perform the following operation. Hardware of Booth algorithm. A numerical example of Booth algorithm is shown for n equals 5. It shows step-by-step multiplication of -9 into -13, which equals +117. In the above table, QR register is set to 10011 and QN+1 are cleared to 0. The LSB of QR register and QN+1 is checked. That is, 10 performs subtraction of the multiplicand, takes 2's complement of the multiplicand and add it to the accumulator. Perform arithmetic shift right with AC, QR and QN+1 register and decrement the counter. When LSB of QR register and QN+1 is 0, 1 performs addition operation with the multiplicand value to the accumulator. When LSB of QR register and QN+1 is both 0 and both 1, perform arithmetic shift right operation directly with the register AC, QR and QN+1. Repeat the above operation until SC is 0. When using Booth's algorithm, you will need twice as many bits in your product as you have in your original 2 operands. The leftmost bit of your operands, both your multiplicand and multiplier, is a sign bit and cannot be used as part of the value. Decide which operand will be the multiplier and which will be the multiplicand. Convert both operands in 2's complement representation using X bits. X must be at least one more bit than is required for the binary representation of the numerically large operand. Begin with a product that consists of the multiplier with an additional X leading 0 bits. Example of multiplying 2 into -5. Reverse the operation and multiply -5 into 2. The numerically larger operand 5 would require 3 bits to represent in binary 101. So use at least 4 bits to represent the operands to allow for the sign bit. Use 5-bit 2's complement. -5 is 11011. Multiplier. 2 is 00010. Multiplicand. Example continued. The multiplier is 11011. Adding 5 leading zeros to the multiplier to get the beginning product 00000111011. Step 1 for each pass. Use the LSB, least significant bit, and the previous LSB to determine the arithmetic action. If it is the first pass, use 0 as the previous LSB. Possible arithmetic actions. 00. No arithmetic action. 01. Add multiplicand to left half of product. 10. Subtract multiplicand from left half of product. 11. No arithmetic operation. Step 2 for each pass with example. Perform an arithmetic right shift ASR on the entire product. Note, for X-bit operands, Booth's algorithm requires X passes. Let's continue with our example of multiplying -5 into 2. -5 is 11011, multiplier. 2 is 00010, multiplicand. Add 5 leading zeros to the multiplier to get the beginning product 000001111. Initial product and previous LSB 000001110. Note, since this is the first pass, use 0 for the previous LSB. Pass 1. Step 1. Examine the last two bits 000001110. Note that the last two bits are 10. Subtract the multiplicand from left half of product. Example, Pass 1, Step 1, Arithmetic action. Place result into left half of product 11110, 11011, Pass 1, Step 2, ASR, Arithmetic shift right. Before ASR, 11110, 11011, After ASR, 11111, 01101, 1. Leftmost bit was 1, so a 1 was shifted in on the left. Pass 1 is complete. Example, Pass 2. Current product and previous LSB 11111, 01101, 1. Pass 2, Step 1. Examine the last two bits of 11111, 01101, 1. The last two bits are 1, 1. Do not need to perform any arithmetic action. Proceed to Step 2. Pass 2. Step 2. ASR, Arithmetic shift right. Before ASR, 11111, 01101, 1. After ASR, 1111, 10110, 1. Leftmost bit was 1, so a 1 was shifted in on the left. Pass 2 is complete. Example, Pass 3. Current product and previous LSB 11111, 10110, 1. Pass 3, Step 1. Examine the last two bits of 11111, 10110, 1. The last two bits are 0, 1. Add the multiplicand to the left half of the product. Pass 3, Step 1. Arithmetic action. Place result into left half of product 00001, 10110, 1. Pass 3, Step 2. ASR, Arithmetic shift right. Before ASR, 00001, 10110, 1. After ASR, 00000, 11011, 0. Leftmost bit was 0, so a 0 was shifted in on the left. Pass 3 is complete. Example, Pass 4. Current product and previous LSB 00001, 11011, Pass 4, Step 1. Examine the last two bits of 00000, 11011, 0. The last two bits are 1, 0. Subtract the multiplicand from the left half of the product. Pass 4. Step 1. Arithmetic action. Place result into left half of product 11110, 11011, 0. Pass 4. Step 2. ASR, Arithmetic shift right. Before ASR, 11110, 11011, 0. After ASR, 11111, 01101, 1. Leftmost bit was 1, so a 1 was shifted in on the left. Pass 4 is complete. Example, Pass 5. Current product and previous LSB 11111, 01101, 1. Pass 5, Step 1. Examine the last two bits 11111 01101. The last two bits are 1 1. Do not need to perform any arithmetic action. Proceed to step 2. Pass 5, step 2, ASR, arithmetic shift right. Before ASR, 11111 01101 1. After ASR, 11111 10110 1. Leftmost bit was 1, so a 1 was shifted in on the left. Pass 5 is complete. Final product. Completed 5 passes on the 5-bit operands. Dropping the previous LSB, the resulting final product is 11111 10110. To verify the correct answer, convert the 2's complement final product back to decimal. Final product 11111 10110. Decimal value -10, which is the correct product of -5 into 2. Division algorithm. The division process illustrated in the example consists of divisor in B register and dividend in A register. Divisor consists of 5 bits and dividend consists of 10 bits. The 5 MSB of the dividend is compared with the divisor. Since dividend is lesser than the divisor, we try again to take 6th bit of a register and compare it with the divisor. The 6-bit number is greater than the divisor. Put 1 in the quotient register Q. Then the divisor is shifted 1 bit position to the right and subtracts the dividend. The difference we get after the subtraction is called partial remainder. The process is continued comparing partial remainder with the divisor. If the partial remainder is less than the remainder, put 0 in the quotient register, otherwise put 1 in the quotient register. Flowchart of division algorithm. Division hardware. Flowchart of division hardware. Division algorithm final. Flowchart of division algorithm final. Hardware implementation of signed magnitude data. Consists of 3 registers and 1 flip-flop. The register QA holds the dividend and register B holds the divisor. Set SC to the number of bits of the divisor. Shift left EAQ registers and perform subtraction, which is in the form of 2's complement addition with B' plus 1 to the accumulator register. Check E flip-flop is set to 0 or 1. When E is set to 1, Qn is 1, and the above operation is repeated. When E is 0, set Qn as 0 and add B register value to the partial remainder of A register. In the above 2 cases, after checking E flip-flop, decrement SC value. When it reaches 0, stop the process. Otherwise, repeat the above step. Divide overflow. The division operation may result in a quotient with an overflow. This is because the quotient register Q and remainder register is finite, that is 5-bit in nature. The quotient consists of 6 bits since the first comparison of the dividend is greater than the divisor. Therefore, to handle overflow condition, use flip-flop to hold the overflow bit. When the dividend is twice as long as the divisor, the condition for overflow can be stated as follows. A divide overflow condition occurs if the MSB of the dividend is greater than or equal to the divisor. Another problem is the division by 0 must be avoided. Overflow condition is detected by using special flop called divide overflow flip-flop, DVF. Occurrence of overflow. In some computers, it is the responsibility of the programmer to check if DVF is set or not after each division. If DVF is set to one branch to subroutine, it takes the corrective measures such as rescaling the data to avoid overflow. In some older system, Occurrence of overflow will stop the execution of the operation. This condition is also known as divide stop. In some systems, to provide interrupt request when DVF is set. The most common corrective measure is to remove the program and type an error message explaining the reason why the program could not be completed. The best way to avoid a divide overflow is to use floating point data. Hardware algorithm. The hardware divide algorithm is shown in the flowchart. The dividend in A and Q and the divisor in B. The sign of the result is transferred into QS to be part of the quotient. A constant is set into the sequence counter SC to specify the number of bits in the quotient. Conclusion. In this chapter, we have covered the following aspects of computer arithmetic: addition and subtraction with sign magnitude data, multiplication algorithms, hardware algorithm and Booth algorithm, division algorithm.